gather round and let me tell you the tale of two LEGO space explorers, Red and Blue, who investigated a strange structure on a desolate moon. Just after they entered the structure, there was a blinding flash of light. When their eyes had readjusted, they discovered that Red had somehow shrunk and Blue had somehow grown. Surprised as they were by this strange new spatial anomaly, they did not notice something making a delivery. Blue turned around and said, "How did this helmet get here?" "Well, it's the wrong color for me, but it looks like it would suit you." "Yes," Red replied, "except that it's about 50 sizes too big." "Well, pass it over here, maybe I can double up on helmets." So Blue picked up the huge helmet and in the low gravity of the moon, gracefully passed it over to Red. They were both shocked to see the helmet shrink as it sailed across the room, landing in Red's hand at the perfect size. Their confusion about what was going on was short-lived, however, as they discovered that this was a trap laid by the robot snakes of this moon to disorient their prey. Pinned against the wall by the mother robot snake, Blue watched helplessly as Red was dragged away into the darkness by the baby robot snake. Mother seemed to be training Baby on hunting space explorers, because she then let Baby have Blue as well. As Blue was being dragged across the trap and away, Blue shrank just like the red helmet had. Hey, perhaps this isn't a baby robot snake after all. And here we must leave the tragic tale of Red and Blue. But what is actually going on? I don't have a real spatial anomaly on my desk, so let's rewind and find out. As you may have guessed, that blinding flash was hiding some trickery. This is the real shape of the room you see after the flash. Of course, Red and Blue were always the same size, it's just that Blue was closer to the camera than Red. We are so used to seeing boxy rooms that have horizontal floors and vertical walls that it's hard for our brains to imagine that something else might be going on when we see what appears to be a box. And I showed you the boxy version of the room first to help sell you on the box shape, before swapping it out for the distorted room. Here's a behind-the-scenes shot of the bit where Blue is dragged across the room. The illusion is so effective that even seeing this, when I look at the view from the main camera, my eyes still tell me that Blue is shrinking. This optical illusion is called the Ames room, named after Adelbert Ames Jr., who constructed the first of this kind of distorted room. As with many optical illusions, the trick is that without stereoscopic vision, and without being able to move your head around, it's not really possible to tell how far away things are from you. If you move the points of something along the lines of sight from your eye, it's very hard to tell that anything is changing. This is more or less how I designed this distorted room. I started with the ordinary box-shaped room, then moved all of its points along the lines of sight. To be a bit more precise, let's get into the math behind these transformations. If you've done any 3D computer graphics, you've probably used 4x4 matrices for rotating and translating objects. You put the 3x3 rotation matrix you want to use in here, and the vector you want to translate by goes here. Then there is the mysterious fourth row. Here's a way to think about what the first entry in that row does. Let's move that number just a little, from 0 to 1 over 100. The shape changes in a sort of perspective-y way. We get something called a projective transformation. If we extend the edges of the transformed room to make lines, they all meet at this point here, let's call it P, which incidentally has coordinates 100, 0, and 0. If you put your camera at this special point P, the transformed room looks like a grid. It's the same as what the original room looks like if you look at it orthogonally along the x direction from infinitely far away. If we apply the inverse projective transformation, then it reverses the effect. That is, if you look at the transformed room orthogonally, then you see what the original room looks like from the point P. This is useful for us because if you're in the orthogonal view, it's easy to come up with transformations that move points along the lines of sight, because the lines of sight all just point in the x direction. That means that we can change these numbers however we want without changing the orthogonal view. Then we can apply the original projective transformation to turn the orthogonal view back into the view from P. The combined effect of all of this is that we have moved points of the room along the lines of sight from P. And that's how I designed the distorted room. Well, and then there was lots of experimentation to figure out which numbers to use to get the effect that I wanted. To record the video, I needed the rooms to stay put while I was repositioning the LEGO minifigures and the robot snakes, so I printed a base that I could firmly attach to the platform that everything sits on. The two rooms have legs that slot into holes in the base, and yes, I know, the room still moves around a bit during the video. I have a much greater appreciation for the effort and skill that goes into stop-motion animation after making this. Alright, that's it. Thanks for watching.